Okay, so the meeting is now being recorded. Uh, so, in the interest of time, let's get started. So, today's talk would be on how to efficiently scale up semantic segmentation models to high resolution images. So, we already have quite a bit of. Am I audible?
Yeah, I can hear you.
Those of you who have joined online, maybe if someone could confirm, I'll go ahead with that. Uh, yeah, okay. Okay, so I'll go ahead. Yes. Uh, okay, so yeah, so the idea is how do we efficiently scale up the existing semantic segmentation models to high resolution images. So we already have quite a bit of deep learning models which work well for obtaining semantic segmentation of images, but then they don't really scale up directly, or in other words, we can't really use them directly. So there are a bunch of reasons. So in this talk, we are going to look at one way to solve this problem. So broadly, the outline of today's talk would be as follows. So first, I'll briefly describe high-resolution image segmentation. I mean, it's very similar to what you see, the regular image segmentation, semantic image segmentation, but just that you deal with a lot more number of pixels. And then I'll mention a few existing approaches and the issues with them. Then we'll see a very simple yet surprising result, which is which we are going to, which is the main work that we have done. So what we do is we kind of, so broadly, your image segmentation, the models require two types of information. So we kind of decouple them to make use of the existing models for low resolution image segmentation, and then build a very simple yet powerful segmentation model. So then that will be followed by some empirical analysis of why the idea works, and then some results on when to use the pipeline that we propose. So with that, I'll conclude the talk. So what exactly is the problem of ultra high resolution semantic segmentation? So you can think of an image. So we all know what a image segmentation problem is. At each pixel level, we are expected to label the pixel, what kind of object it belongs to. For example, on the image on the left that you see, broadly it has three types of, you can always go further down, but broadly it has three types of objects. So one is person, second is bicycle, third is background. You can always break it down further into road, etc., etc. But let's say we have three classes. So at each pixel level, the goal is to somehow predict the labels of all the pixels. So each label being one of the three possible classes that I just mentioned. So this I can break it down as a combination of two binary segmentation problems, which would be bicycle versus rest or person versus rest. So likewise, I can always think of image segmentation problem which with multiple classes, and I can break it down as solving several binary classification problems, right? So this is very well known in literature. The problem with ultra high resolution image segmentation is that the pixel image sizes are quite large, in the sense that each image has at least 2000 by 1600 pixels. So this is like really large, and the main issue that we have here is that in order to use the existing models, suppose say I want to use say a deep lab series or PSPNet. So these are like some of the popularly used segmentation models, which do give us pixel level predictions of what semantic or what object it belongs to. But the problem with directly using them for these ultra high resolution images is that Firstly, they require a lot of memory, which would not be feasible. In fact, the problem is all of them would require a GPU memory linear in the number of pixels. So this is a big bottleneck. And the second issue is that most of these, not all, but most of these methods, they are supervised, meaning while training, you require at a pixel level the labels of each of the images. So for example, if I go back to an image like this, then I need to provide, for the input, for training, I need to provide 2000 by 1600 into number of images that I'm using for training. So if each image is of at least this much size, then effectively, I'll need so much effort to provide pixel level annotation. So this is also a problem, but the main bottleneck here is requirement of memory. So this is the challenge that is posed. So what could one possibly do? So one simple workaround would be, instead of working with the whole image at one go, I would probably, break it into overlapping cropped versions of the images, and then somehow predict the pixel labels and fuse the outputs. So this, while this can be done, the problem with such an approach is it will destroy the image context. Meaning, you will fail to capture some of the global details. So this is, this does not work well in practice. So building on this idea, so if at all some global details are missing, how can I somehow get hold of the global details? So if I can use this multiple overlapping crops alongside somehow, if I can capture the global information, then that's one way to solve this problem, right? So this is what some of the existing approaches do. And again, these involve deep neural networks. What they do is they have a large network. So there are like two branches broadly. So this is a very particular one particular architecture which is used in practice. So it's called a global local network, or GLNet in short. What it does is one branch downsamples your large image, the UHD image. So this is some kind of blurry version of your original image, and the other branch takes several crops, and then each of these branches, they somehow share some features, and then there is a lot of complex architecture involved. So finally what they do is, in short, if I have to put it, they by sharing the feature maps, somehow they arrive at good predictions. So while this does give decent results, the problem with such methods is that I don't really know if at all I have to use this same network for a different data set. How do I tune my hyperparameters? So this is one of the problems that you have if you use these methods directly. So another approach that people currently use are, instead of using the whole image. So since we run into memory issues, what they do is, so if I simply downsample the image, that would be like a uniform downsampling. That would give me blurry results. So which is why somehow if I can figure out what patches of the image are important, I will sample more points from such patches, and then less points from patches where there are no real, so where it's easy to predict the objects, right? So this is something like the dots that you see here. So these are like the sampled pixels. So this is, if I can non-uniformly downsample the pixels, somehow I can solve the issue of using, or solve the issue of the GPU bottleneck. However, the issue with such methods would be they would still require the ground truth at a large. I need to know the ground truth annotations of all the pixels uh, at the ultra high resolution level. That's one issue. Second is that once I non-uniformly downsample my pixels, the issue would be you would no longer be able to use the convolution operators in the sense of your usual neural networks. You will have to modify them somehow if at all you plan to use the traditional CNNs. So this is your second issue. So there are other methods too. but broadly they fall into these two categories as you have just seen. So one would be so the first one that we just described was the fusion of local and global information, where the local information comes from the cropped patches. That was your GLNet, and then the global information comes from your uniformly downsampled image. So this is one category. Second category is somehow figure out important patches and non-important patches, and then do higher percentage of sampling in the more important patches, so that you don't lose out on the finer details. But most of these, the problem would be two. One would be the requirement of ground truth annotations. Second would be how do I tune my hyperparameters? So that's a big question that's unanswered. So what we would do here is, so we would take a different approach. Somehow, I don't really want to start from scratch, meaning I want to use the existing neural networks which have already been trained for low resolution images, and then extend those methods uh, to arrive at a good segmentation result for these high resolution images. So how would we do that? Instead of working around with two different branches, one as local and one as global, somehow we plan to decouple the local and global information. So how would we do that? So we start with uh, a downsampled version of the original image. So meaning, I just downsample the image, the UHT image that I have uniformly, and then see what happens if I use a typical neural network approach that we already have, something like a deep lab series or the standard ones, all of these. Any of these can be applied. So once I downsample my UHT image, we no longer have memory issues, but then I won't be able to capture all the details, right? So of course, some information would be still captured in my, and when I work with my downsampled image, and some information would be lost. So what exactly is the information that's still available after I downsample? So here is what we have. So this is an useful observation. This is fairly trivial, but it's an important observation. So if the downsampling rate is not too high, meaning if the resolutions of the downsampled image and the UHT image are comparable, or in other words, if the tiny objects do not vanish in the downsampled image, then I would have the same set of semantic labels as that of the original high resolution image. So if I just go back to my example of bicycle, so if I blur this image, not by a great extent, but to a certain extent, I would probably see a blurry version of a bicycle, blurry version of a person, and the background. While I will lose the boundary details, it's unlikely that I will miss out on the whole object. So this is important because this is effectively, if I downsample my image and work on that, I will get some sort of global information. So regarding the semantics, so that's point one. Second is that if at all, this image does not contain so many people, but if at all this image contains like 2 or 3 different people, then I will, even after downsampling, I will still see 3 instances of people. So which means that if I have to put it formally, so there is a bijective correspondence between every semantic instance. So if there are like 2 bicycles in the original image, I will still see 2 bicycles in the low resolution estimated segments, right? So this is the global information that I'm going to use from the downsampled image. So what I would do is I would downsample the image uniformly, apply existing techniques, and then first get hold of these kind of information. So what all semantic levels are there in my image and how many corresponding to each of the semantic instances. So this is something that I can capture by simply with no extra effort. All the existing models, if they are trained on the same domain, meaning if I work with natural images, take a neural network that has been trained on natural images, use it directly. Use it on the downsampled image, obtain this information. So all I need to do is somehow get the, so the details, whatever would be missing from the downsampled images have to be accounted for. So the next question that obvious thing to ask would be, what information would be lost if at all I work with a downsampled image. So the answer is very simple. Only the finer details would be lost. Say for example, I broke down the segmentation problem into a two-class problem here. So originally this had a person as well, but if we view the uh, problem as a two-class segmentation, bicycle versus no bicycle, then the left-hand side image that you see, so this is the ground truth. While the details are very clearly visible on the ground truth, if I work with a downsampled image, if I infer my labels on the downsampled image and then upscale it back to the same scale, then effectively the result would look something like this. So as you see here, this is like a smoothened version. The right side image, if you see, the details are not as good as what you see on the left side. For example, the brake wire between the handles, it's kind of missing. Also, the spikes in the wheels, so they look very blurry. You see that that's kind of clear. So all you need to, sorry, yes, sir. So all you need to account for is somehow make sure that start with these basic estimates and then somehow correct for the finer details. So in fact, there is a simple experiment that can be done. So these are the plots that you see. So these are the number of, the proportion of labels that are incorrectly inferred as a function of distance from the nearest object. Or in other words, most of the errors that we are making by simply working with the downsampled image and upscaling them is near the object boundaries. So that's kind of clear here because only at places where the pixels are close enough to, bicycle versus uh, outside bicycle. So those are the places where we make errors. So if a pixel is very much in the interior of background or within the bicycle, there is a very low chance that you make errors by simply upscaling your estimates. So this can be, in principle, yes. Yeah, so x-axis is distance from the nearest boundary pixel. So a boundary pixel is nothing but so a pixel that's on the bicycle that's right adjacent to background, or a pixel in the background that's adjacent to bicycle. So if I go one pixel further up, that's at a distance 2. One, sorry, distance 1, 2, so on, right? So you go farther away from a boundary, the higher the distance. So the y-axis that you see here, this is the relative frequency of incorrect labels. So yes. It will be clear in a while, so it will still be the same. So incorrect versus correct. So this is just incorrect versus correct. So what we do is your base estimator, it would still be able to, it gives you probabilities, right? So typical neural networks have some sort of a softmax layer. You get some sort of probabilities. The first and second probabilities are the most important. So those would correspond to objects or on either side. So you won't get objects that are somewhat farther away.
After upscaling, upsampling, how are you determining the label of the other points?
Yeah, I'll come to that in a while. So I haven't said that explicitly. So we do some sort of a bicubic interpolation. So yeah, I'll come to that in a while. So this is the idea. So the errors that we are making are mostly near the boundaries of the objects. So the left and right plots are exactly the same plots, but with different neural networks. So the left one uses one of the Deep Lab series, model from Deep Lab series. The other one is FCN8. This is another popular segmentation model. So this is the hint that, so this is something that empirically tells us why to, go ahead with our approach, or why it works. Oh, okay. Yes, sure. Definitely. Yeah. So Okay, you mean okay in Shannon entropy? Okay. I'm not sure if there is a very specific uh, principles that say how to downsample. Yeah. Oh, I'm not aware of any theoretical works which say how much should be downsampled, but we have done some experiments and to verify how far we can go using our pipeline. If at all, I use the downsampled version to predict the UHT. I need to check that. To answer your question, I need to check if there is a principled way to decide. Okay, that is the Nyquist. Right. I'm not sure about that. I need to check that. Yeah, so this is why you get our, I mean, so all we need to do is somehow refine the boundaries. So this is somewhat doable because now I no longer have to work with the whole image. Somehow I need to work at the boundaries of the objects. So, but then how exactly do I make sure that my finer details are captured? What I would do is I take the high resolution image and then apply some sort of a learned gradient. So these learned gradients, while the segmentation problem is not scalable uh, uh, with respect to size of the images, learned gradients are easily scalable because these are local information. So these just capture the changes. So what we do is, so here is one kind of gradient that we have used in our pipeline. So this can be changed to any other learned gradient. So this is something that is developed from random forests. So what you see here, the image on the slide. So this provides you a black and white map or a grayscale map. So the darker the pixel, the higher the chance of the pixel belonging to a gradient. So this will somehow make sure that what I'm trying to do here is somehow construct some sort of a barrier so that if at all I, somehow if I can cut down on the labels on the boundaries and then correct for the remaining, I will ensure that I will use these sort of barriers so that my labels do not cross across the boundaries. So this is the global information that this is the local information that I'm going to get from my high resolution image. So the way we decouple the information is work with the low resolution image separately and work with the high resolution image uh, uh, separately, and then get hold of these probabilities and then the base level estimates, and then fine tune them across the boundaries. So again, there are several ways to do it. The approach that we did is, this is just a zoomed version of your earlier image, that just to show you the details. So the left side image is the original image, which contains the bicycle and the background. So the middle image that you see, what we do is we know that only the pixels that are close to boundary are mostly erroneous. So how do we formally take a dig at that, or how do you formally arrive at correcting those labels? What we do is the pixel level. So once we downsample the image and apply your neural networks, we get some sort of probability values for each semantic possibility, right? So what we do is when we upscale the probability estimates, we use what is called as a bicubic interpolation on the probabilities by each semantic. So this is just a interpolation applied across the probabilities of semantics. So each coordinate wise we apply so by each coordinate I mean probability of that particular semantic. So once we do that, what we do is if at all some label I'm not very sure of, what would that be? So look at the top two class probabilities on the interpolated label probabilities, and then see if the difference is not too high. If the difference is somewhat low, that means that the model is unable to predict it with a great confidence. So this threshold is a hyperparameter in our pipeline. So we make sure that if the difference is below a certain threshold, we are going to take another look at it. Or in other words, I'm going to refine the label on such pixels. So if I just remove those kind of pixels, all the white pixels that you see in your middle image are those for which the bicubic interpolated label probabilities of the top two classes are not very different. So this is what you have. So, and then the third image is effectively, so you see three colors here. White corresponds to, these are more or less I'm confident of that they belong to bicycle. And then the gray corresponds to, I'm more or less confident that these belong to background. And black is the area where I'm going to estimate the labels again, right? So, or refine the labels. But we don't stop here. We go one step further to improve our results. So these are again not expensive operations. So what we do is from the pixels that we already obtained. So let's call these things as potential seeds, because eventually what we are going to do is propagate labels from whatever we are very confident of to the other regions. So I don't really use these pixels directly. Rather, I would further trim them down so by using what are called as thinning and pruning operators. So these are like classic morphological operators. So if I apply thinnings, thinning operation iteratively, again, how many iterations to use? This is another parameter. So once I apply a series of thinnings, I would arrive at something like this. So if you look at this carefully, this would have some sort of a skeleton of how the object looks like. So you see some thin strands here near my cursor, or I could zoom it. So these are some kind of thin structures that you see. I can further break it down. While this is not very clear, pruning is something that would further cut down on certain branches here. So these are just operations that make sure that you get good results. But again, so these are well known in literature and not very expensive operations. So we apply a series of thinnings and a series of prunings, and then finally whatever pixels that I am left with. So these are the pixels for which I am very confident of that they belong to the class. So likewise, I do it for the background as well. So if I have a lot of classes, I do it for every class. So the reason why I didn't use all the classes in a single image is that would, this would provide you an idea of what we are doing. Same thing holds for multi-class as well. So within each of the class, I would trim the pixels down using these operators successively, right? So once I do that, I will be left out with the pixels that I am very confident of to use as seeds. So how would I make use of my global information? What I do is I take the probabilities so I take the gradient probabilities. So each pixel I could predict whether or not if it's a gradient, right? So what I would do is I would set the edge weight corresponding to the two pixels that are adjacent to each other. So I can view my image as a 4 adjacency graph. In other words, each pixel is connected to north, south, east, and west, 4 other pixels, right? So this is like a grid graph, 4 grid graph, and then each edge that connects any 2 pixels from the predicted probabilities, whether or not it's a gradient, from the learned gradient, I would construct edge weights like this. So the reason why I do this is I want to make sure that the weights are very low if both the pixels are likely to be gradients. So this is a decreasing function of Pi plus Pj. Both the pixels are on the boundary, both are on the gradient pixel, then I don't want my labels to propagate across. So the way we set these weights is higher weights, the more we propagate. So effectively what I want to do is use some sort of a seed propagation method that propagates labels across higher edge weights. So random walker is one example which we have used. So higher, somehow I need to set up high edge weights for which, I mean, if the pixels belong to the same object, I should have higher edge weights so that the labels get propagated inside of the objects but do not cross across the objects. So that's what I want. So that's the reason, intuition behind setting up these edge weights. So if I have to put them down all together, this is how it will look like. So so I start with the this is the upscaled version of your downsampled or the estimated labels from upsampling your low resolution predictions. That's your top image. So once I do my seed selection, while you cannot see the thin structures of pruning, etc., so the image that you see on top middle is the image that you obtain after doing all the operations that I mentioned. So first we remove the not so sure labels by by setting the threshold on the top two probabilities, followed by thinning, followed by pruning. So I get something of this sort. Then I take my high resolution image and then predict the probabilities that each pixel is a gradient, and then use these pixel probabilities to set up the edge weights, and then use these as seeds. So the white pixels that you see here, so these I'll use them as seeds, and then these edge weights that I just constructed from this equation 1, I will run a random walker to predict the or to estimate the labels of the remaining pixels. So I mean, for around every object like this, not just bicycle, but all the objects that you see in your image, the labels are propagated by I mean, using these edge weights. So then I will get a result that would definitely be better than simply upscaling your downscaled estimates. In fact, this turns out to be as good as the state of the art. So the idea here is not to beat the state of the art, but how do I decouple local and global information? So this is a useful idea that can be used across methods. So again, should I have to use random walker? That's not the only way. This is just a proof of concept that you can work with both the local and global information separately. So here are some results. Performance on benchmark data sets. So classically, I mean, you don't have a lot of high resolution images. So big is one data set which is used by the state of the art. That when we I mean when we completed our article. So this was around sometime mid of last year. So this Cascade PSP net or Cascade net is the article which had the state of the art. So this is Cascade net is nothing but it's again a refinement technique just like ours. So the top 4 methods that you see, these are the baseline methods which are not meant for high resolution images. So the numbers that you see on your column number 2 and column 3, so these correspond to intersection over union. So this is the classic measure to determine how well your segmentation is. So the higher the number, the better. So the numbers that you see corresponding to first 4 rows are you work with the downsampled image and then upscale the estimates. Obviously, they are not going to be very good. So the best of the methods is Deep Lab V3. This is the best among the 4 methods, which is why you see that these 2 are the highest among the first 4. Cascade is a method that Cascade net is a method that improves upon existing methods. So if I start with FCN and then apply Cascade, so this is the results that you get. So likewise for the next 3 rows. So ours is the last 2 rows. By the way, meticulous net that you see in 9th row. So this is a neural network that's developed to handle ultra high resolution images directly. So while the code is not reproducible, the results for a big data set is available. So the current state of the art as of August last year was Cascade net and meticulous net for data set big. So we could show that our refinement method performed slightly better than the Cascade net. So by ours, we mean the usage of random walker and setting up the weights as described earlier. So this is not just a state of the art, but then there are a few other things. I mean, how exactly, when does our method work? and when does it fail. So these kind of things we have done some analysis, which is what follows now. So first thing is that uh, how should I tune my hyperparameters? So that's one question that people ask. If at all there is a paper that produces very good results, if I have to use it on my data set, how would I go about it? So I would want to know if at all my model is robust to the hyperparameters that I use. So the number of thinning operations and the pruning operations are a couple of hyperparameters that we have, right? So in the pipeline. So if at all we keep changing it, the ideal value was somewhere, I don't remember the ideal value, but across a large range around the optimal value, the percentage of pixels selected as seeds, uh, I mean, did not go down by a lot, meaning uh, even if I do a lot of thinning and pruning iterations, I am assured to have at least 88% of the total pixels in the image that I am very confident of. So that's point number one. Second is that among the pixels that I selected as very confident, not a lot of them are false positives. So very low percentage of the pixels that I picked as confident turned out to be bad predictions. So which means that I am not losing a lot of information there. So the plot that you see here is just a log of these percentages. The reason for using a log plot is that otherwise you won't be able to see such low percentages. So that's the reason you see these negative values. So these are numbers less than 1. So all the log values are negative, right? So this is good because uh, all the seeds that I have selected, they are very robust to the number of thinning or pruning iterations that I use. So the second thing that I need to talk about is how exactly how much does my method depend on the gradient that I'm going to use. So if at all, or in other words, if I start with a learned gradient and then corrupt the values, then will my method still give reasonably good results? So to check this, we conducted 2 experiments. So one is from the estimated labels. So what we did is we started with the gradient that we used, and then we corrupted the values of the gradient with Gaussian noise, zero mean at various levels of noise variance. Of course, we truncated the values so that the probability of pixel being a gradient has to lie between 0 and 1. It cannot be negative. So we truncated uh, after adding a Gaussian noise, truncated to 0, I mean, on the lower side. So then we checked how well does the method perform. So even when the noise variance was quite high, the percentage IOU or intersection over union, it did not go down a lot. By the way, the litmus test for how well the model performs would be when I look at only the non-seed pixels, or in other words, the ones that I'm predicting. So what exactly are non-seeds? The ones that are on the, the ones that I'm trimming or fine-tuning. So the inside ones are anyway good. So on the boundaries, am I doing really bad once I change the gradient with some sort of a noise? So the answer is no. In fact, even for non-seeds, even at various levels of noise, it doesn't really go down by a lot. So of course, I mean, if you have too much noise, then nothing much can be done. So the same experiment we replicated for, instead of using estimated labels to start with, what I do is I start with the ground truth labels and then simply, okay. So instead of starting with my estimated labels here, if I start with the ground truth and then trim on the boundaries and then start with the corrupted gradient and see how well the labels propagate. So this is, of course, I mean, this is something that you cannot do in practice because you don't have access to the ground truth, but you can just to see how well your method fares. This is a good experiment to check. So we checked this, and in fact, even for the ground truth refinement with noisy gradient, the answers still look good. I mean, so even up till uh, a level of 0.2, the results did not drop down by a lot. Later on, there is a slow decline and then there's a sudden jump, of course. Beyond a certain level, you can't expect much. That's kind of says that, I mean, you can, you need not work very hard in fine tuning your hyperparameters. You would still be able to obtain a reasonable estimate. So yeah, so far so good, and good things about our pipeline. But of course, nothing works perfectly well. We do have some sort of limitations to our pipeline. So first is, it's obvious to see that if the low resolution image that I work on to get my base levels, if the scaling factor between the low resolution image and the high resolution image is way too high, then the results would be very bad. I mean, in fact, you can see that some of the small objects would be completely lost. At the other places, it would still be not so good. So what we did is we took the data set, big data set that I mentioned earlier, and then we downsampled the image to several levels, and then did the experiment, same set of experiments, and checked how well the intersection over union or the metric is. So if I downsample by a lot, so the longer axis length is, okay, let me just go back. So the longer axis length is 2048 here for the smallest image. So if the longer axis length, if I make it very, very small, so that was of order 2000. So if I make it 30, obviously the results would be very poor. So up till 210, which means 1/10, it still gave good results. So this is not too bad. So this is one issue. Of course, you need to know. So depending on what kind of images you are working on, natural images do not contain a great level of details as some other images in some other domain. So this scaling factor of 10 need not be the same if at all you are working on a different domain. So that's something that practitioners have to be cautious about. And second is that it also has another limitation is that it depends a lot on the low resolution estimator. So this is again, you might have already observed that so across the four baseline methods that we had, the answers were different. I mean, so FCN, if I use FCN as my baseline method, the results were much inferior when compared to using DeepLab V3. So of course it depends on my base estimates. In fact, to illustrate on how bad it can get, if at all my base estimator does not predict, so here is an image of a person holding a dog. So the ground truth labels of the dog are given as shown in second image. So all the white shade corresponds to dog, and the black is other than dog. So rest of the image, right? So, but then if I apply DeepLab V3, somehow the bottom portion of the dog is not detected. So if I start with such a sort of estimate and then trim down and then use our pipeline, of course there is no way I can obtain or reconstruct the lower portion of the dog. So this is an obvious issue with our pipeline. So it depends a bit, way too much on the low resolution estimator. So this is something that has to be, people have to be careful of if at all they plan to use this. So second, another limitation that we could see is that if at all you have objects of, objects with low area and high perimeter. So these are typically called as low isoperimetric quotient. Or in other words, if you fix the number of pixels, for a fixed number of pixels, if the perimeter of the object is way too high, then most of the pixels would fall close to the boundary. That's kind of obvious. So once I work with those, when I trim down on the possibilities or the confident pixels, I would be left not with many pixels, which means that even after I reconstruct, so the first image is the original image that you see on top. The second image on top corresponds to the ground truth. So this is a flower vase that we are trying to predict here. And then if the base estimator gives me something like this, then no matter what I do, I won't be able to reconstruct these thin objects well. So this is another issue that we have. with our pipeline. So, yeah. So to conclude, so what exactly would I want to convey here is that decoupling your global and local information, it leads to efficient usage of what we already have. Instead of starting from scratch, you can use the existing methods efficiently to obtain segmentation for high resolution images. So the advantages that we have with our method is that we don't really require ground truth annotations of the corresponding high resolution images. Of course, I mean, if I plan to use, so the low resolution annotations, I'm assuming they can be obtained. Even if not, we can use transfer learning. For example, the deep lab that we used, it's just a transfer learning. As long as I know what domain I'm working on, uh, and I have some trained model on that, on the low resolution counterpart, I can use that. So that's one advantage, which is not the case with most of the other existing approaches. So second advantage, which not many approaches offer, is that we just have a very few hyperparameters. So the details, I have not mentioned all of those. Remaining, most of the details are available on the paper. So these are very easy to tune, and then advantage is that you don't really have to work very hard. So the results are robust to the choice of hyperparameters that you use. So you can get away with reasonable estimates without really doing a lot of hard work. So another main key insight that we have is that we know when exactly our approach is applicable, and I mean, we have characterized some sort of necessary conditions. So the limitations essentially say that when you do not have such conditions, you can apply our pipeline to get reasonably good results. Otherwise, you might run into trouble. So this is very important to know, because if I'm given a new data set, how would I go about it? What method to use? So most of the state-of-the-art methods, I mean, it is very difficult to figure out when it's applicable and when it's not. So I'd like to stop here. There are questions I can take.
That we use is a uniform.
Yes. So the downsampling method that we use is a uniform downsampling. So we don't really. So the reason for using uniform is it's easy to do it. Second is we can use the other existing methods, because all the convolutions are just the same convolutions, right? So otherwise, you'll have to work with some sort of modified convolutions to take care of that sparsity. Are there any questions from the online attendees? Uh, okay, so there are no other questions. Then I'll stop here. Thank you. Ah. Oh, okay.
Who is the first author in that?
Siddharth is he was a B student here. Now he's doing masters in UCSD. Can we use the same idea to generate images? Uh, what kind of, you mean deep fakes kind of images, or you mean uh, 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 okay. Um, I don't know. I mean, the way I see it, so this is we only get No, we can't really generate images, so we mostly use this is more like a refinement. um, okay, generate low resolution image. um, no, texture would be very difficult to get with the current state of the method, right? Because so this will just smoothly fill things, the labels. So it will be more like a flat, lot of flat zones. You can't really get that fine level label details. At least I cannot see that. Okay. Uh, are there any more questions? Uh, okay. So if there are not, I'll stop here. Thank you. Okay. Thank you.